Okay, so welcome everyone to the second session. So we'll have two talks in this session, and the first is by Jed Pixley. So please take over.
Thank you. Yeah, so hello everyone. Thank you for having me at this wonderful workshop. I'm really having a great time, learning a lot. It's a very inspiring place to be. So today I'm going to talk about some work we've been doing on infinite randomness, and in the spirit of this conference, quasi-periodic, infinite quasi-periodic fixed points in the context of measurement-induced phase transitions. And the quasi-periodic part of this is not on the archive yet, but hopefully will be soon. So if there's any additional details you'd like, I'm happy to talk offline. Okay. Okay. Yes. Okay. Okay. So let me just start by thanking my collaborators. A lot of this work was done by my student Aiden Zavallo, who joined the real world at Prudential. I also have very nice collaboration with Justin Wilson and Sarangala Prakarshanan, who are both in the audience, as well as several other collaborators. And then the quasi-periodic work I'll talk about actually came out of a visit from Gal, who visited my group in September, his advisor, Snare Gizit from the Hebrew University. Okay, so I'm going to start by motivating this problem by talking about these entanglement transitions in the context of measurement-induced phase transitions that have already been talked about prior to this conference by, I think, Sarang. And then from that, I'm going to talk about the stability of these transitions to static perturbations. We're going to show that these are unstable to static perturbations. They flow to some infinite randomness fixed point that we can characterize quite accurately with numerics and describe with RSRG, real space RG, and they get pretty good agreement. And then in the last part of the talk, I'll talk about how we can introduce the so-called non-Pizot quasi-periodic structures to induce large fluctuations in quasi-periodic systems to make them actually relevant perturbations, even though you might have naively thought they were irrelevant. So hopefully this is of interest to everybody here. This is known since the 90s, but I feel like it's been lost in the literature. Okay, so this talk is going to be about a problem where correlations are insufficient to describe the phenomenon. Okay, so correlation functions are not enough. So we have to do something else. And the main player in this talk is going to be the entanglement entropy. So just to set everybody on the same footing, we're thinking about a system that we divide into two parts, A and B, and we trace out region B, and we talk about the entanglement of region A. And what we're really interested in is how that entanglement scales with the size of that region. So to define a weakly entangled region would be scaling like the area of that subsystem. This is characteristic of ground states of gapped Hamiltonians, which has been rigorously proven in 1D, and a lot of recent results in 2D, though it's not fully proven. And then there's also highly entangled states, volume law-like states, where the subregion is highly entangled with region B. And these can happen generically just by running generic Hamiltonian evolution on a state, assuming H is generic, so not like many body localized or anything like that. Or we could take a quantum circuit and hit it with random unitary gates, and the long time limit, we're going to generate an extensive amount of entanglement. Okay. And in this talk, I want to think about phases, dynamical phases of matter that I can characterize by this entanglement structure. So I'm going to be thinking about two different phases that are area law-like and volume law-like, and we're going to be thinking about quantum critical points between those two. And what we do know about critical points, at least for ground states, that they acquire log correction. Okay. And we're going to see something like this happens in the measurement transition, but the coefficient is a very different quantity physically as well. Okay, so the workhorse for this talk is going to be quantum circuits. They've already been introduced, but I'm going to try to introduce them very concretely. And there's three kind of models that are at play here. So the generic quantum problem we all want to solve is taking random q-qubit gates for spin half and basically running the dynamics. Okay, this is discrete evolution, and this cannot be simulated with classical efficiency. So you have to rely on intuitive ideas or finite size scaling, et cetera. We also have a limit where you can take the on-site Hilbert space to infinity. This is a semi-classical limit, really maps to a classical problem in one higher dimension, and this is an analytically tractable system. And we also have so-called stabilizer circuits or Clifford gates, where these can be stimulated with classical efficiency, but these are some other non-trivial semi-classical limit, which is inherently very unstable to any other type of gate choice outside of that group. Okay, so those are generating our entanglement. Now we want something to compete with that entanglement to drive a phase transition. So we're going to start measuring the system with some probability P. Okay, so what these green dots mean, it does not mean I make a measurement. It means I come in with probability P and make a measurement. So let's say I roll my dice and I make a measure where all these X's are. Okay, So now my unitary dynamics is no longer unitary because I have to insert these Krauss operators corresponding to these projectors due to the measurements and renormalizing the state after the projector, which produces a nonlinear effect on the wave function. Okay. So as a result, you have to keep track of this measurement history. And that's actually a rather deep statement that you have to know the measurement outcomes to see this transition. If you don't know the measurement outcomes, you cannot see this transition. That's equivalent to dissipation. Okay, so let's start from this controlled limit because it's a really anchoring point for your intuition. So taking Q to infinity basically maps to a Q state Potts model, which when you take Q to 1, it maps directly to percolation. And what that means here is what the entanglement dynamics, the entangling unitaries are doing is they're building a connected network in time and space. Okay? And the measurements are coming in and they're cutting it apart. But the measurements are sufficiently dilute when P is small, such that if I cut my system in half, I'm going to have an extensive amount of entanglement. Whereas on the region where I measure a lot, I'm going to cut this network apart, and it's going to be disconnected little clusters that can no longer be fully connected. And that means that this transition actually falls into a percolation universality class in the limit of infinite Q. Okay? And this is just a picture of classical percolation, bond percolation in space-time. This predicts a logarithmic growth of the entanglement. It also has universal exponents that you know analytically in this dimension to be exactly 4/3 with an emergent Lorentz invariance. So while this is a conformal field theory, it's a rather exotic one because the central charge is actually equal to 0, and this is known as a logarithmic conformal field theory. Okay. So this is a percolation. Let's come back to the quantum problem. Okay. So the quantum problem, we have to do numerics. And so the question that we are asking ourselves in 2018 is, does this fully quantum problem belong to a different universality class? Turned out to be a very hard question to answer. Let me just show the progress to answer that. So the first thing we needed to do was find a method to accurately estimate the location of the critical point. And the expectation of a log L scaling at the critical point, which you know from percolation, we also knew from Clifford's, which I haven't shown you, spoils any kind of finite size scaling you want to use on the entanglement entropy. So we introduced it, we borrowed from Kitaev, Preskill, and Levin and Wen this notion of this tripartite mutual information, which we're able to show cancels this log L at the critical point. And as a result, if I were to plot this object versus P for several system sizes, I should expect a crossing of the transition. So I can do that for HAR, okay, and I see a reasonably crossing. So if I focus here, that's where I'd estimate my critical point. And I can only go to 24 spins, and so you might question this. But then we can do the same thing with stabilizer circuits, which we can go all the way out to 500 spins, okay? And we can check the accuracy of this approach. And even at 24 spins, we get a PC, which is very close to what you get from 500. So this finite size scaling approach is actually quite sophisticated, and we believe that the HAR finite size corrections are not sufficient to destroy this picture, okay? So we have a way to estimate that transition. If you look at the critical exponents, they look remarkably similar, and they look close to percolation. So within the accuracy of our computation, we cannot discern these universality classes apart, okay? And so we looked at other exponents, also eta, and at this stage, when we wrote this paper, we could not tell the universality classes apart. We had reasons to believe that they are distinct, but it was not a sharp statement. So this is a whole nother talk that I'm not giving, but we were able to use methods borrowed from percolation applied to these non-unitary circuits within transfer matrix approaches and Lyapunov spectrum to really determine that these are distinct universality classes. With one defining feature of the HAR or the fully quantum problem is that the logarithmic conformal field theory you find is multifractal, which is a rather rare field theory to identify, but Clifford is not multifractal, and same with percolation. We're also able to get the accuracy of the exponents quite well. We can discern them apart, and there's a so-called effective central charge, which also separates the three universality classes. So there are 3 log CFTs, and the quantum problem introduces multifractality. Okay, so this is where we're at. So now we introduce the main questions I'd like to address in my talk, okay? So 2 main questions. The first one, is this transition stable to static perturbations? So can we apply ideas from scaling theory that we know well from critical phenomena to this problem? And then if it is a relevant perturbation, can we then find new types of universality classes thanks to quasi-periodicity that live between the fully static disorder problem and our measurement-induced phase transition? And the answer will be yes to that, okay? So let's go ahead. If there's any questions on the motivation, happy to take them now. Great, okay. So let's go on to adding static disorder. And so this is something we actually were asking right away. And so how do we understand basically the stability of this transition? And you would like to basically apply what you know from standard stat mech, namely the Harris criteria, that nu should be greater than or equal to 2 in one dimension, but nu is 1.3, and so static disorder should be a relevant perturbation, okay? And as a result, the question is, where does this transition flow? So if you go back to percolation and you add static disorder to percolation, it was already known to flow to infinite randomness. So we knew right away we had to use really large system sizes to be able to see this phenomenon, okay? So I'm gonna use Clifford simulations for the rest of the talk, okay? And seeing this in HAR is probably close to impossible. Okay, so now what we're gonna do is we can introduce static disorder in many different ways. It's a choice. We're gonna introduce it through the measurement profile. So the idea is the value of P that I generate is not translation invariant, but it's time translationally invariant, okay? So it's random in space, fixed in time. And we wanna amplify rare events. So we want a strong tail on these probabilities. So we think about a random number between 0 to 1 to the n, and n is gonna be our parameter we vary, because that fixes my average measurement rate. Okay, so I just show you this distribution. It has a very large tail to large P. So it's natural to expect this to induce rare regions. It's going to give us enough oomph, so to speak, to see the infinite randomness. Okay, and the first conclusion you had to reach is that averages of these quantities are no longer very meaningful because you have broad distributions at the transition. So here I'm showing the distribution of this tripartite mutual information. As I vary the measurement rate, you can see it's a very broad distribution that develops a non-trivial tail. If you look at the two phases, the volume law phase just becomes broader and broader as you increase system size, whereas the area law phase also has this very non-trivial tail. And if you look at this value at I3 equal to 0, you can see there's actually a fundamental distinction in the scaling on the two sides, namely in the volume law phase, in the thermodynamic limit, the probability to find I3 finite should be 0 because it's fully connected, whereas in the area law phase, it should go to 1. So if you plot the probability of I3 equal to 0, you have a very nice crossing, and you can then collapse the data, and you get an estimate of nu, which is very close to saturating the bound. Okay, so that's the first estimate of PC. We had a couple other methods to do it that all agreed. I'm not going to totally get into that here, but we're quite confident in the estimate of PC. Then we started studying the phase diagram of this model. Okay, so now instead of volume law and area law, I should be dominated by Griffith's physics near the transition. So what does that mean? So let's look at, these are individual realizations of the entanglement entropy as a function of the cut, and each different curve is a different time trace. As the curves become darker, I go later in time. And the color down here is my value of P. So if this is blue, P is very close to 1, and if it's red, P is close to 0. So as you can see here, it's a very large measurement rate that produces a so-called entanglement bottleneck, things we hope to see from MBL for several years. We never really see them. You see them beautifully here. This produces these entanglement bottlenecks. And if you then average these quantities, the average entanglement then should no longer be ballistic. Okay, and that's precisely what we see, and that power law is then related to 1 over this dynamic exponent z. So the data for 1 over z on this side of the phase transition, we can extract from the average entanglement scaling. We cannot do that over here because it's area law. Okay, so this is the first signature that we have Griffith's physics on the volume law side. So now we have to see the analog on the area law side. So we come to the area law side, and now you have these local thermal bubbles, so to speak, of large entanglement. And so how do I probe dynamics in this phase? I want to probe these bubbles. I want to probe these thermal regions. And so what I'm going to do is I'm going to bring an ancilla qubit, an external qubit. I'm going to entangle this ancilla qubit with my circuit at some point in space and time. I'm going to look at the purification of that ancilla. If I tried to do that in the volume law phase, it would be an exponentially long time. It would never purify. But in the area law phase, I mean, never purify in my finite size simulations. In the area law phase, I should purify on reasonable timescales, but it'll be controlled by these thermal regions. Those are going to be the longest timescale to purify. So we can probe this purification time of the ancilla to extract a dynamic exponent on the area law side. So these data points are extracted from the purification time of the ancilla, which is dominated by these thermal regions that are maximally entangled locally. Okay. So coming now to the critical point, if you look at the critical point, you have this rather unusual scaling of the entanglement entropy. It goes like square root of L. Okay, I haven't seen this before myself. But if you look at the entanglement dynamics in time, it scales logarithmically. Okay, and so to get out a dynamic exponent at the transition, you can use a relaxation rate or basically find the time from each system size when it relaxes. So you find the time, so you run a very big system that never relaxes, and we could never get this to relax we couldn't wait a really long time, of course. But then you can follow this curve back and extract a relaxation time. This relaxation time follows very nicely this dependence, exponential dependence on square root of L, and that stressed exponential also seems to hold in the volume muffix. Oh, yes. You're not putting Griffiths in by hand, you're putting in the strong dichotomy between P's by hand. So the picture is that your universality class is unaffected by your choice of that distribution, but being able to see the infinite randomness on these sizes is hard. And so we looked at several distributions, and this one you could see it most clearly. Yeah. But we're not putting in the rare regions by hand. We're just letting that have a tail, which generates them. Yeah. Thank you. Okay, so now we want to probe this so-called activated dynamical scaling. I don't know if you're familiar with this, but the dynamic exponent z actually diverges with the correlation length related to this so-called activation exponent psi. Okay, and so how do we probe this? So we try to, again, couple an ancilla and look at the purification of this ancilla at the critical point. Plotting with log t over L does not collapse the data, but applying this scaling hypothesis to the data, you can collapse it in terms of log t over L to the psi, and you see very nice collapse. Oh, sorry. You see very nice collapse, and so we now have estimated these two exponents that characterize this infinite randomness transition. Okay, and we had a very nice collaboration with Roman Vasseur, who worked out the real space RG computation for this model, and the limit of infinite Q basically maps to a Q-state pulse model I already said, but now you have columnar disorder, and Roman was able to extend this RSRG into the replica limit as Q goes to 1, and you find actually really amazing agreement between the numerics and the real space RG. Okay, so if I convinced you that the measurement-induced transition is unstable to static disorder, and it flows to this infinite randomness fixed point in a quantum circuit. Okay. Any questions on this part? So finite Q is not physical, because it's, at finite Q, you could do it as, oh. Sorry, go ahead. So in this problem, the Q at infinity is required to map it to a Q-state Potts model. So you don't have a Potts model at finite Q. So you don't even know what to do, really. The stat-mech model is untenable, so to speak. Just as hard as doing the numerics, unfortunately. Yeah, thank you. Okay.
Can you think of this as doing some percolation?
Absolutely. So we also had classical results on percolation, and it also has an infinite randomness fixed point, but a distinct universality class, which I can. Oh, sorry. Go ahead.
When small q goes to infinity.
Yeah. When q goes to infinity, that is percolation. So this is like the percolation infinite randomness. Yeah. Thank you. And it's surprising that our Cliffords matched so well with that. I mean, that shouldn't have necessarily been true. Yeah, thank you. Okay, very nice. So now I want to kind of turn this on its head, okay? And I want to try to find transitions that lie between the two that I just told you about, okay? And I can, and let me show you how to do that, okay? So let's now add a quasi-periodic perturbation to this fixed point. This is known as the Luck criteria, which is probably less familiar to several people, but the idea is when I have a clean fixed point, that clean fixed point or whatever fixed point is stable, provided if I add quasi-periodicity, provided this relation holds, where this beta is a wandering exponent, okay? And so in most people's experience with quasi-periodicity, they would write down a quasi-periodic function like Aubrey-Andrews potential or something, right? But this has a zero wandering exponent, which means that this is an irrelevant perturbation to this fixed point. So I can just run my numerics now. I don't expect broad distributions, and I reproduce very nicely the universality class of measurement-induced transition. Very nice consistency with what I'd expect. Okay. I'll get there in 2 slides. Yeah. Okay, so now how do we tune beta? Okay, so the way we're going to tune beta is we're first going to move away from smooth to discrete words, from smooth structure to discrete words, but Fibonacci won't be enough. So Fibonacci will still have beta equal to 0. But let's start with Fibonacci to get a feeling, okay? So Fibonacci words, you have 2 letters, 0 and 1, and these inflation rules are basically the Fibonacci sequence. And you can generate so-called Fibonacci words iteratively in this process, okay? So this is one way to represent this word building. A more concrete or systematic way is represented as so-called substitution matrix, where this notation is rather opaque. So let me just tell you what it means. So this is basically the number of zeros get mapped to zeros. So the number of zeros get mapped to zeros is 1. The number of zeros that get mapped to 1 is 1. Number of ones get mapped to 0, 1. Number of ones get mapped to 0, 0. Okay. So this matrix controls beta. Okay. And so the substitution matrix is going to have two eigenvalues, a bigger one, a smaller one. And it turns out that the size of the word growth is controlled by lambda plus. It's just like an inflation factor. But the fluctuations of the word in space are controlled by the smaller eigenvalue. And the wandering exponent then can be computed. So basically, if lambda minus is less than 1, beta is equal to 0, these are so-called P-Zod structures. But if lambda minus is bigger than 1, you can compute beta from here, okay? So you can engineer a matrix to give you the beta you desire and then figure out the words it needs to generate. You can go backwards, okay? And so let's just do this for Fibonacci. So to do this for Fibonacci, you find beta 0, so this is not going to do it, okay? And again, you could run the numerics like we did, and you get the same conclusion that the same universality class survives, the measurement-induced transition comes back for you, okay? So now let's try to start generating these strong fluctuations in non-P-Zod structures. So what we're going to do to show you how this works, basically what I'm going to do is I'm going to count the number of ones in the word. That's going to be n of s. And I'm going to consider a collection of words all of the same size L. And I want to look at the fluctuations of these words as I grow them in size. Okay. So what this also tells you physically what this wandering exponent means, right? It's telling you that if beta is 0, these do not grow with system size. So the fluctuations of the quasi-periodicity are bounded. These are the quasi-periodicity most of us are familiar with. But in principle, beta can be finite. And indeed, if I look at these fluctuations as a function of system size, this is Fibonacci, it does not grow. A random walk is at a half, but I now can find these two that sit between them. I could actually find a whole family, an infinite family of them if I so wanted, but they're discrete family, not smooth. And those would be examples of relevant, so-called relevant quasi-periodic structures, provided I choose them the right way. So how do I make them relevant? So to make them relevant, I want to choose beta such that I go beyond new MIT, which would mean that this is now a relevant perturbation to my measurement-induced transition. Okay, that's the key logic here. So by varying beta, we can introduce relevant perturbations to this transition that are not random, but quasi-periodic. And the question is, what is the universality class of this fixed point? Okay. So let's take beta as 0.385. So this predicts a bound of about 1.63. And you can obtain this from this rather complicated substitution rule. Okay. And the way we're going to now introduce this to the measurement-induced transition is if the letters are 1, I'm going to set it to P, but if the letters are 0, I set it to 0. So it's a 0 or P, and I'm going to vary the value of P, okay? And if we now apply the same ideas that we developed in the previous part of the talk, which is looking at the probability of I3 equal to 0, you have a very nice crossing, and when you collapse the data, you find a nu, which is very close to saturating the bound. So it looks like it's flown to a new fixed point. This new fixed point is in between the measurement-induced transition and nu of 2, which is infinite randomness. And it seems to be an infinite quasi-periodic fixed point, though I haven't convinced you of that yet, but I have convinced you, hopefully it flows to a new fixed point distinct from the measurement-induced transition. No disorder. I'll come to that in the end. Yeah, thank you. That's a very nice question.
So if you take the ratio of the critical exponents, do you see that that's also changing, or is it fixed to the normal disorder?
Great question. That's in the summary. I'll show you that. Let me come back to your question because it's a very nice question. I have a slide for that question. Okay, so let's now look at the entanglement scaling. So we have this square root of L from the random problem. So this motivates a scaling ansatz like this, okay? And you can apply this to the problem, and you have a very nice data collapse provided X is equal to beta. So the fluctuations of the entanglement growth are controlled by my wandering exponent, okay? And just say in the back of your mind, random walk, beta is a half, okay? So it's growing like a random walk in the random problem, and it's growing like this non-trivial quasi-periodic structure in this problem. Okay, so I want to conclude that the transition, I have the growth like L to the beta. Now I can look at dynamics. This is how I can convince you it's infinite quasi-periodicity like. So we can use the same procedure. So first off, these are really big systems and you can saturate them. So the dynamics is much faster than the random problem, but it's still slow. Okay, so based on these relaxation times, we can pull out a relaxation time versus L to the beta, and it fits a very nice straight line. So this relaxation time is exponential in L to the beta. You can also now compute psi a separate way from the ancilla qubit entanglement, okay? And you get nice data collapse provided you're at large enough system sizes to see the appropriate dynamical scaling, and we get psi is equal to beta. Okay, so let's put this all together. So we've identified two different types of transitions, but I can characterize them all in terms of beta. So beta for a random problem is a half, completely characterizes my universality class, whereas quasi-periodicity, beta is tunable. Okay, so I've found an entire family of quasi-periodic fixed points in between the measurement transition and the random one. All right, and now as I'm just going to conclude really with a question that Sriram just really asked. And so let's now sit to be beta is less than a half. Okay, and so the question is, how do things flow? So if I'm starting from my measurement-induced transition, the first part of my talk showed it flows to infinite randomness. And then the second part showed how this flows to an infinite quasi-periodic fixed point. But now I could ask the question is, if I added disorder to this problem, what happens? And if provided beta is less than a half, this flows off to infinite randomness. So indeed, my main question of the talk is, can I identify a whole family of universality classes that lie between the measurement-induced transition and infinite randomness? I have, okay? I've characterized them, and it's a very interesting open question to take beta larger than a half, where you can make this stable to disorder, but that was really hard to reach strong conclusions in that regime, and that's actually an open question for future work. So yeah, I'm going to end a little early, but I'm going to conclude. So basically, I showed you that the measurement transition is a novel dynamical transition in the structure of the entanglement. I didn't talk about it, but this is not visible in correlation functions. And Justin Wilson's talk, who is going to come in the next session, is going to describe that aspect very nicely by adding control. I also showed that this transition is unstable to static disorder and flows to an infinite randomness fixed point. So in devices like superconducting qubits that have disorder, I mean, they don't have very many qubits, so they never see this, but theoretically, it should be unstable. So for example, trapped ion systems where this disorder is not intrinsic would be a much more stable setting. And then I showed you that by generating non-piezoic quasi-periodic structures, we're able to identify a whole family of infinite quasi-periodic fixed points that we characterized and showed that they're distinct from infinite randomness, but everything's controlled by the wandering exponent, or how strong things fluctuate in space. Okay, so thank you for your attention, and I'm happy to take questions.
Questions?
So is the statement about when you add disorder on top of non-piezo, so if you frame it in terms of stability, so it's again unstable to that addition of static disorder?
So it's this, so this new bound is 1 over 1 minus beta. So if beta is less than a half, this will be less than 2. And so it's always unstable to disorder. But in principle, I can generate non-piezoid structures with beta bigger than a half. There's no reason why I can't do that. Numerically, the system seems to phase separate, so I don't exactly know what's going on there. Still working on that. But in principle, if I could, then I should be able to find quasi-periodic fixed points that are stable to disorder.
So whatever you have shown, this is unstable.
That's right. So everything I focused on was beta less than a half, living between the two fixed points. Yeah.
More questions?
Just a quick thing. The point I3 equals 0. Is it what's special? Why that point?
Yeah, I mean, it's more of it's a great question. I mean, this was kind of empirical, then reasoned through separately. Let me just kind of show you that data. Sorry, let's go back to that. But the intuition is clear. So the intuition is basically that in the volume law phase, in the thermodynamic limit, I could never find a disconnected circle. Like it's always going to be entangled on that circle that I cut into 4 pieces. And so in the thermodynamic limit, this has to go to 0 at I3 equal to 0. Whereas in the area law phase, you can of course cut it apart. And so this can go to order 1. That's the logic. And then we just looked at the data and it crossed. And then we looked at several other diagnostics that I'm not showing you. They give us the same PC. So it was like, yeah, it was reasoned through, but it's, yeah. It's not an obvious quantity, yeah.
I was just going to one time, I think on the RG flow picture, is there a fixed point at the origin as well?
I didn't draw stable fixed points.
Oh, okay.
I only drew unstable fixed points.
But it wouldn't be the.
But yeah, absolutely. So let me, sorry. Yeah, I mean, absolutely. If I drew stable fixed points, then I would have had the area law phase and the volume law phase is stable. So this would have had flow. You know, you have a stable fixed point here, that's volume law, and then one here, that's area law.
But then it's unstable in the disordered. It's unstable in the
Well,
disordered.
no, actually, this is still volume law. Yeah, so I don't, yeah, this is schematic. I mean, it's, don't put it at 0. I mean, put it somewhere at infinity at finite couplings.
Okay.
Do you see that? Does that answer your question?
Yeah, maybe I sort of need to
Okay.
draw it myself.
I just kind of sketched it. I didn't, yeah, just a sketch of the idea. But I think, I mean, this notion, I just want to make a point that this notion is incredibly general. I mean, you can think about single particle problems, and such physics also survives in localization phenomenon. You find several universality classes in between the two. They don't have to be infinite randomness like or anything, but I think this is a very interesting general perspective I wanted to say at this conference, because not everybody's interested in quasi-periodicity, but I think the people here are.
Oh, yeah. Oh, okay. No, it's okay. I'll get some exercise.
How about the free fermion case? I mean, the free fermion, the measurement transition,
That's a
what
great
happens to this?
Well, so that's like BKT.
Yeah,
So it should also be unstable, I would think.
stable.
I think it's unstable. But
Unstable.
that doesn't have a volume law phase. It says log
Yeah.
phase, so the phase might even be unstable. I don't know, actually. I've not thought about that. That's a good question. I haven't thought about that. I mean, here the volume law phase just becomes, you know, very, very long relaxation, highly, highly entangled. In the fermion case, yeah, I don't know. That's a great question. Not sure. Yeah. Maybe somebody should work on it.
Oh, okay. Yeah, maybe it's more general. So you can look at other nonlinear sort of correlation functions which are nonlinear in density matrix, right?
Absolutely,
So,
absolutely.
So have you sort of looked into any such things?
We've looked at these squares. I mean, the paper by Nahom et al. They write it down. They didn't compute it, but if you look at these, you know, you take a connected correlation function, square it, and average over measurement outcomes, then you have a peak. But the peak is weak. So on Haar systems, it's like a very weak signal. But figuring out how to get it from correlators, I think you certainly could. But we didn't explore that too much. Yeah. Beyond I mean, seeing the peak was like an indication, but then we were able to get these crossings in I3 and also this ancilla qubit. You can also use that entanglement entropy at late times, and that also can have a crossing. Not in the infinite randomness case because of the slow relaxation, but in the standard Lorentz invariant one. That's actually, I think, a very nice metric. Easier to compute too than I3.
Any other question? Okay, I don't see any. So let's think yet for another very interesting talk. So let's thank him.
Oh, okay. Using that.
Yeah. I've sent you the.
Yes.
Shumilan. AV at ICTS. Sumilan, SU. It didn't go or what?
Arun, Arun. Stop.
No, this is not. Oh, I sent the wrong talk. No, this is the old talk I sent earlier. This is not the one I sent now. I'll check. Yeah. But the Zoom.
Okay, so the next talk is going to be by Shumilan Banerjee.
Okay, thanks, Arnab. So sorry for this delay. And okay, so let me start by thanking the organizers, of course, for giving me this opportunity in spite of the fact that I have never really driven anything quasi-periodically or periodically. So okay, so I'll be talking about something maybe loosely related to which Jed talked about, but from a very different perspective. And this is related to measurement-induced transitions, but not really directly. So I'll discuss a quantum model which might have this measurement-induced transition, but we are not going to study it in the quantum limit. So it will be ultimately a classical calculation, as you will see. But I'll try to motivate it from a quantum limit. Another thing is, some of you might have heard this talk, so sorry to bore you again with this. Okay, so first acknowledgement. So all the work has been done by Shibram, who might be here, and you can find the details in this paper. So I don't need to make this introduction here, but just to sort of just to remind you. So I think the idea is to study this kind of what I'm broadly calling chaotic to non-chaotic phase transitions for a particular reason, because that's what I'm going to discuss. So I'm just putting all these different things in this broad category. And I think it sort of started from the interest of people in understanding this many body localization transition, where you have essentially this phase diagram, highly debated though. That you have a ergodic to MBL phase transition, and this transition is characterized by entanglement, one of the unambiguous ways. So you go from a volume law to area law if you tune disorder, or it might be possible also with the energy density if there is a many body mobility edge. And also you can see this in some entanglement growth, other thing. But the main point, I guess, here is that people got interested into this new paradigm of phase transition, which Jed talked about, which is entanglement transitions. And that led to all these discussions I think we are having, all these beautiful developments over this last few years on looking into quantum circuits, initially to start with unitary evolutions, but then going into putting measurements. So this is the same picture taken from the reference which I'll show. I mean, this is a familiar reference. So you have this some spin up state, and then you are applying 2 qubits gates. So with this 2 qubits gates, this will entangle the system as you go on in time. But you sort of disturb this entanglement by doing some projective or weak measurements in each interval of time with some fraction of size on which you do these measurements. Okay, and then and if you tune this rate of measurements, or you can tune if you have a measurement strength or even the unitary strength, then you can actually induce a transition. And all this, there are many references. I'm not citing all of those. And eventually you get this nice, beautiful transition that as a function of this measurement rate, you can go from this volume law to area law with some interesting critical phases in between. And there are many works also, so not only on this kind of gates, unitary gates with measurements, but also Hamiltonian systems. And even also weak measurements and other things. So for example, for non-interacting fermions, interacting bosons, small systems, some bosonization description. Of course, it's not a measurement-induced transition, but effect of measurements on sort of low energy states. So there are a lot of works like this. So now in this talk, what I'm going to do, I'm going to sort of take a kind of a step back and trying to see that is there a meaning of talking about a classical limit in a Hamiltonian system of this kind of measurement-induced transition. And what I'm going to discuss is actually, I'll try to sort of motivate, although I'll not be able to really show it because we have not done any calculation in the particular model in the quantum limit that I'll discuss. But what I'll try to show that you can start with a quantum model of measurements of interacting system, and then go to the classical limit, take the classical limit in a controlled way, Essentially, it will be a classical limit by taking h bar going to 0 in this model. And then so you'll see that there is a so what happens in this classical model, it will actually become a stochastic Langevin dynamics type model, where the measurement actually directly lead to noise and dissipation. Okay, so I'll show that the measurement strength actually determines the noise strength in this Langevin equation. And then in this kind of equations, there are such transitions known as classical nonlinear dynamics, which are called synchronization transitions. So I'll actually show that by tuning this noise or dissipation strength, which is same in the measurement strength, if you start thinking with the quantum limit, you will actually have a transition where in classically your phase, so there will be one phase where you have less noise, or in other words, weak measurements, weak strength of the measurement. Then you will have classical trajectories, which actually will, if you start two trajectories very close by initially, so at a later time, they will deviate away from each other exponentially with this Lyapunov exponent, which will be positive. However, if you go on increasing this noise or measurement, you will eventually get to a situation where these trajectories, rather than going away from each other, sort of try to come close together. And in fact, the Lyapunov exponent become negative, and this is known as the synchronized phase or stochastic synchronization. And I'll try to argue that this something like that might be happening in many of these measurement models. Okay. Okay, so so I already gave the outline. So this is sort of the way I'll progress. So I'll start with actually a quantum model of continuous weak measurements, and then I'll try to take the limit, the h bar going to 0 limit analytically, and we'll derive a model which will actually will see that our very well-known stochastic Langevin equations, where the noise or dissipation strength will be exactly equal to the measurement strength in the quantum limit. And then I'll show that in this Langevin equations, this is of course nothing special about this measurement. I mean, this Langevin equation will be a standard Langevin equation, and I'll try to argue that any interacting system, this Langevin equations actually has a transition, okay, which we generally don't see any other dynamical properties, but you can see if you look into chaos. Okay, so that's what I'm going to do, and I'll actually show a transition. I'll show that this transition has some nice finite size scaling properties also. All right, and I'll also look to sort of contrast these scenarios. I'll also look into two different types of model. One is a non-integrable, completely non-integrable model, like some quartic oscillators, coupled oscillators, and another would be this integrable, interacting integrable TODA model, and I'll try to contrast how this happens in these two different models. Okay. Okay, so let's start. So first, the quantum model of continuous weak measurement. So we are essentially trying to generalize a model, and probably this has been done earlier also, many people. So I don't know the literature very well. So the way we started with is this well-known paper by Caves and Milburn, where they wrote down a weak measurement model for a single particle. Okay, so what we are going to do. Here we are going to generalize it just to many coupled oscillators. So essentially this one-dimensional oscillator, which is, let's say, described by this model, where you have some kinetic energy and some interacting potential energy between the oscillators. So it will have some quadratic term, quartic term, etc., etc. Okay, so this is the what I'm going to call the system Hamiltonian. And the measurement. So let me now describe what measurement we do on this. What is the protocol? So this is the idea. So what you do, so you are trying to do measurement in interval of time tau. So basically in this discrete time tau, you do the measurement, and you do the measurement on all oscillators, okay, simultaneously. So this doesn't matter. The measurement I'm doing is commutes with each other, so it doesn't matter. I can do it simultaneously or one after other. And the way I do this measurement is by coupling this system in this kind of a kicked manner with some ancilla or the detector, or what is called a pointer. So basically for each instant of time n, for each oscillator I will have a pointer, which is a quantum particle with a position and momentum, and the momentum of this pointer is described by this p hat indexed by in. Okay. So at each instant of time n, I have these pointers of the detector. So effectively what is happening is I'm starting with some initial state. I'm doing this measurement in this discrete interval, and between these two discrete times, the system evolves with this original unitary evolution. Okay. And then just before the measurement, Tn minus 1, what I am I'm already ready. I keep these detectors which are generated in a Gaussian. So each of the detectors are generated in a Gaussian state. And this the strength of this, which is related to the strength of the measurement, is indicated by this parameter sigma. Okay, so this is just before the measurement. Then at Tn, what we do, we basically this term will now work at T equal to Tn, and then this coupling will switch on instantaneously and then switched off at that instant of time. And then at Tn plus, I make the projective measurements on the position of these meters. Okay, so so this is why this is a weak measurement. So then I'll get a set of readings. So this is the measurement system. So you can of course write it the density matrix evolution using some unitary part and some Krauss operator, some measurement operators. And of course, this can also be written as a standard quantum state diffusions for pure state, etc. But what I'm going to do is I'm going to actually write down a path integral for this and take the classical limit. So here there is one extra bit here. So I'm going to take a particular. So there is another extra thing here, which is that I also put following Caves and Milburn. I also put a feedback in the system. So essentially, what the feedback does, if you don't put the feedback, this particle, the momentum will sort of diffuses away. So what you try to do is by putting a displacement operator, you try to bring it back so that the momentum just go to infinity. Okay, so that's what this feedback or the feedback does. And then what I'm going to do is I have two parameters, measurement related parameter. One is this sigma, which is this width of the Gaussian wave function, and another is tau, which is how often I'm doing the measurement. So the limit I'm going to look at is when basically I take this sigma going to infinity, basically very weak measurement, very broad Gaussian, but I do it too often, tau going to 0. And then I keep this delta finite. Okay, so that's the limit. I can write a path integral for this system, and you can write down a Keldysh path integral for this dynamics, this exact density matrix evolution for a given realization of xi. Okay, of course the quantum problem should be studied. We have not studied it. So what I'm now going to do is going to take the classical limit of this Keldysh path integral. Okay, so this is a standard way. So what you do is in Keldysh I have these two branches, plus and minus. So they're in showing this here, plus and minus. And then what I do is I essentially do a Keldysh rotation. I write it as a combination of, so this should be classical anyway. So I write it as a combination of classical and quantum variable, this whole path integral. And then the way you take the small h bar or classical limit is by expanding in this quantum component, which is effectively expanding in h bar. Okay? And it turns out to have any interesting physics. You cannot take the strict classical limit in this model. You have to take a semi-classical limit where h bar is not 0 but small. Okay, so if you take completely classical limit, this gives some trivial results, infinite dissipation essentially. Okay, so if you do this, what you will find that you will find your favorite Langevin equation that we have studied for very long. Okay, and here you will have a dissipation strength gamma, and you have this noise, Gaussian noise, and the strength of this, I'm just writing this as gamma into T. Okay, so there is some strength. I'm just defining some effective temperature here. And this noise strength is related given by h bar square by delta, and it turns out to take the classical limit meaningfully, you have to think of also scaling this delta as h bar square. Then only there is a meaningful limit. Okay, so this is the noise strength, and you can obtain the effective temperature. So effective temperature goes like square root of h. The main point is that your noise strength here is entirely determined by the quantum fluctuation parameter h bar and your measurement strength. Okay, so it looks like the standard Langevin equation with some effective temperature, but it is exactly like, but here the noise is entirely controlled by quantum fluctuation and measurements. Okay, so if you don't have, yes. No, so that has actually given this gamma. So that is the origin of this dissipation term. So if you don't give that, this term will be absent. Okay. So this gamma is actually the strength of this feedback. So this is where the gamma appears. Okay, so this is how you give the feedback. So if you don't give the feedback, it will not settle into a nice steady state. So with this gamma, what happens is if you satisfy a fluctuation dissipation theorem, so will eventually lead to a classical Boltzmann distribution that will be your non-equilibrium steady state of this process. Okay, where the temperature is determined by this. So I don't know how much time do I have? I'm going too slow for. You have around. Oh, okay, good. Okay. Yeah. Yeah. You are not using the information of the outcome. Yeah, so that's a very important question. So it turns out that in this limit, this information doesn't matter. It sort of go away. So there is actually, there is some technical detail here. So if you sort of try to write down the path integrals of various objects like OTO, so I'm going to discuss OTOC. Okay. So it turns out that matters, it sort of couples two trajectories. There is some additional term which sort of couples these two trajectories, which comes from integrating out these measurements in this kind of nonlinear object. It's not very different. So that's why it's not clear how exactly it is connected to the kind of thing Jade and other people are talking about, right? So it turns out in this classical limit, this I'm not integrating or averaging over the outcome. It doesn't matter. Okay, so it sort of doesn't come out in this calculation. So I don't completely understand how it sort of gone. It could. So once you have derived it, there is no difference, right? So what I'm going to now show is that even in a caldera Leggett but you will have a transition. Okay. Okay, so the question is, as I said, that is there a transition in these things? Of course, this is a 1D or coupled oscillators Lange equation has been studied, and we have never seen any transitions in standard quantities. So certainly there will be not a transition in any standard dynamical quantities like diffusions and other things, right? You have to look into something else. So that's what I'm going to do. So I'll start with the case where you have the noise or measurement strength 0. So that you only have in the classical limit, you just have the Newton's equations. Okay. So I'll start with this and then try to go into the case where you have non-zero gamma. So as I said, I'm going to look into two models. So one model is the standard non-integrable model, similar to Fermi-Pascal. Not exactly, but so you have this quadratic and quartic term, and another model I'm sort of going to contrast with is this integrable Toda chain. Okay, so this is the so I'm just now, since it's a classical model, I just simulate this thing in classical. Okay, and the quantity that we are going to look at is essentially just this Lyapunov exponent, and the way we just look at it sort of get some spatial information. This is a standard thing which has been done recent years. Starting with work at ICTS. So what you do is you take two initial conditions, and I give a small difference between the two initial conditions, but the difference I give locally, so that I have some local information. Okay, so for example, here at 0th site, I give a small difference between the positions of these two trajectories, and then I just evolve. And for reasons we can look at other differences, but we look into this momentum difference. Okay, so basically at each site I, which is some distance away from the initial site, you look into how this quantity, which is called a classical OTOC or decorrelator or whatever you like, you just look into this difference. Okay. And here, as I said, that the long time steady state is a thermal initial state conditions which are drawn from basically generated by some Monte Carlo or some Langevin dynamics to be initial thermal distributions. So that's what we look into. Okay, so first let's look into this case where you have this non-integrable model but no noise, or in some sense no measurement, if you would like to think that way. So then what you find is that so this is gamma equal to 0. All I am varying is the interaction strength u. So what you will find that if you have u equal to 0, this model, of course, so I am plotting log normal scale. So so if there is exponential growth, there should be some linear region here. So what you will find that if u equal to 0, it doesn't have any exponential growth. Only if you make u finite, then immediately you will get some exponential growth. Okay, so that means there is a positive Lyapunov exponent. So the non-interacting model doesn't have any chaos. And you can also see the light cone spread here. So you'll have a light cone and that will define you a butterfly velocity. So you can also do the same thing in the Toda chain without the noise. So Toda chain turns out that, I mean, you don't really have any linear region in Toda chain. So that means the Lyapunov exponent is not positive, okay? And it probably is 0. But however, in the Toda chain, you have still a light cone. I mean, inside the light cone, it might look weird, but it still has a light cone, okay? So that means the Toda chain has a finite butterfly velocity, but no Lyapunov exponent. Okay, so now let's put the noise. So noise, when you put the noise strength, so then you have to also think about how to define this difference. Okay, because now you have two trajectories. If you put completely uncorrelated noise in these two trajectories, then there's nothing to compare. So it turns out the right thing to do is to take correlated noise. So both the trajectories for each oscillator at each instant of time exactly has same noise. Okay. And it turns out if you then calculate the same quantity, as I discussed earlier, so this is a meaningful quantity to look at. And in fact, this is the result. So if you take the quartic oscillator, you indeed find, so this is for a fixed value of gamma. Then you average over noise. Yeah, you average over noise realization or initial condition. So in our case, we generally do initial condition average, but you can do that also. Yeah. So what you will find for gamma equal to 0, in fact, so now I have fixed a gamma, I am varying u. So you can see that when interaction is small, then the Lyapunov exponent is actually negative. This quantity is actually decaying. And as you increase the interaction, then it becomes chaotic. Okay, so what is happening is you have a chaotic transition, lambda L greater than 0 to lambda L less than 0. Here I am varying u. But you can also vary, fixing u, you can vary gamma and you will see the same kind of transition. So it's basically what matters is u by gamma, right? So there is a chaotic transition. So in some sense, this transition is happening because of the measurement strength, which is the noise strength in this model. Okay, so this is Lyapunov exponent. You can in fact see this, how for different values of gamma, as you change u, so it goes to positive to negative below at some critical value. Some critical UC, and another thing to note here is that there is very little finite size scaling effect on Lyapunov exponent, okay, in this transition. And you can see the similar transition as a function of gamma. So what happens to the light cone? So you can also look at the light cone. So this is in the chaotic phase where U is large. So you have a light cone, and as you go through UC, so that light cone is destroyed. Okay, so the butterfly velocity goes to 0. So you have also a transition in the butterfly velocity. It goes to 0. In a continuous fashion looks like, and you have more or less within our numerics more or less same value where it goes to 0, where the Lyapunov exponent goes from positive to negative. All right, so you can actually look into the finite. So as I said, the Lyapunov exponent doesn't have much finite size scaling, but you can look into the dependence of the system size dependence on the butterfly velocity. At least whatever data we have, we could collapse into by the scaling form. You could collapse into this kind of thing, and you can extract within this limited numerics, you can actually extract some critical exponents. And these critical exponents, generally this kind of transitions, even classical system has been studied by many people and in cellular automata in other systems. And typically they find directed percolation or some Kardar-Parisi-Zhang type universality class. So this doesn't match with, okay. That is the thing. And of course, as I said that, is there any transition in any other dynamical properties? So the answer of course is known. I mean, we know that there is no transition. So what I am showing here is just looking into a single particle diffusion, looking into the mean square displacement. And the mean square displacement of a single, so it's like a polymer monomer diffusion. Okay, so this is like a polymer essentially. So we find that when you have no noise, then this is a diffusive form. You have some diffusive growth of this mean square displacement, and then there's some diffusion constant. And as soon as you put some gamma, if you put some noise, so it becomes subdiffusive. Okay, this is actually known from polymer monomer diffusion. Okay. So these are well-known results. So that, but it doesn't have any transition at any value of gamma or u, right? So this transition you only seeing this. So what is this transition? Okay, so actually when we started working on it, we didn't know about any of this literature. So after getting all these things, we realized that this kind of thing people have studied in nonlinear dynamics. But what they did, they didn't do it on a Hamiltonian system. So they took some coupled map lattices. So essentially, you have some nonlinear map at each lattice site, and you couple them, and then you look into this kind of butterfly velocity and Lyapunov exponent. And in fact, in those cases, they found there is this transition, and this is called stochastic synchronization. So by noise, you are synchronizing the trajectories. Okay, so essentially, it turns out that the transition we are finding is also same kind of transitions, but now in a Hamiltonian system, and this is fairly generic because this model we took nothing special really, right? So you would expect this to happen in any other model also. So that's the thing, and certainly this is some measurement into phase transition. Whether this is the transition that we are interested in the quantum limit, that I don't know. Okay, because we have not studied the quantum limit. So how it connected. So just last sort of slide before I end. So what happens in the Toda chain? So Toda chain is kind of something maybe expected, but maybe interesting also. So as I showed you that Lyapunov exponent for Toda chain for the gamma 0 limit, which is the integrable limit, is 0. Okay, so this is 0. So now as soon as you put some noise, what happens is that this noise initially makes it chaotic. Okay, and this is in fact known for few particle system by work by Kutzan and others, and that actually grows like gamma to the power 1/3 or something. So we get something very close. So it initially grows, and then it has a peak, but eventually at very large gamma, it has to go through the synchronization transition. So it does go through that, and it will again go from positive to negative. Something interesting also happens for butterfly velocity. So butterfly velocity, as I showed, is not 0 at integrable point, it is finite. But if you try to approach the butterfly velocity from this side, from gamma positive, gamma non-zero side, it turns out it almost like have some kind of a singularity there. Okay. Of course, ultimately finite system probably it will come down continuously, but it looks like that these two approaches are different. Okay, and then the other, so essentially there are two transitions here, one in the integrable limit and other in this. Okay, so let me sort of end, so I'm done basically. So end with this. So this is the same as my summary. So essentially what I tried to show is that you can start with a very generic quantum measurement, continuous measurement model, and derive this stochastic Langevin equation, which just looks like any standard Langevin equation, which will even get from Caldera-Legette-Bath. And this system has a synchronization transition, very generic transition. Now in this particular quantum model, this parameter that controls the transition, which is the noise, is same as measurement strength. So you have this transition. Of course, we have looked into a certain way of taking small h bar limit. So the question is really to add axis here, okay, and try to see this entanglement transition that is there in quantum limits, how it goes into this thing. Is there any connection to this? I don't know. Okay. So with this, I thank you for your attention.
Questions?
Thank you for the very interesting talk. I was just curious at the synchronized phase. Can you characterize it with correlation functions?
Yeah, so there are some, you can sort of calculate these active sites, not really correlation function. I mean, we have not done. The people who have done, they have sort of active sites and other kind of standard things. How much, like you start with many sites different, then whether they grow or how they grow,
like they do
those kind of things.
Kind of thing. Okay.
Yeah.
Thank you.
Yeah.
Yeah. So, I have. If I keep increasing gamma, there'll be some regime where things will start becoming linear because of very high dissipation, right?
Yes.
So this synchronized phase is something between. It's still non-linear, but it's still non-trivial.
Yeah, so this gamma going to infinity, it will just go to some minima, potential energy minima, right? So like steepest descent. The dynamics is essentially becoming a kind of a steepest descent type.
No, yeah.
I mean, essentially it will go to zero actually. So it will, all the particles will go to the zero displacement. So freeze to the zero displacement. Yeah, so in
So
between you have this.
right.
Yes.
No, gamma going to infinity is fine, but I'm saying even before that,
Huh.
there is a regime where effectively u over gamma is very small.
Right.
So any model would just become like harmonic oscillators, right? Like a harmonic network. So is there a regime before gamma infinity, but after gamma c, where it just becomes like a harmonic network, no matter what you
Well,
start?
we have not looked into that. See, I don't know really because, okay, we didn't study, but this diffusion that I showed, so it turns out actually very weird thing that in the harmonic limit, and this is known actually analytically. If you look into mean square displacement, even harmonic limit, it looks diffusive without gamma. Okay, but as soon as we put some gamma, we always find that it is subdiffuse. So I don't really know how this, so then it will be a crossover or transition from subdiffusive to diffusive, what you are saying, because in the harmonic limit, you expect it to become diffusive. So I don't know where that is happening. Yeah.
So just a clarification, because I did not understand. So if you would do this analysis for the cosine interaction potential, you would get the standard Kuramoto.
Yes.
synchronized.
Kuramoto, yes. Yes.
So this would correspond to Kuramoto for that potential, right? Or not? Or
No, so we have an extra process here, which is the measurement process, right? So I have a Hamiltonian, so that will become Kuramoto if you use some.
no, but saying also in Kuramoto, you have dissipation.
So I can, rather than putting this quartic and quadratic, I can put Kuramoto model. I don't think that, that will.
You get something different or? Because also there.
No, so there, of course, there is a phase synchronization. So I'm not talking about phase synchronization, right?
More questions? Oh, yeah. In the classical integrable model, I expect the KAM theorem to apply as I go in towards the chaotic regime. So you've sort of canceled that out with your noise. It's destroyed the invariant tori, and you're already.
So actually, this is nice understanding is there in this Jorge Kuchan paper.
Okay.
So basically what happens, this tori, rather than getting destroyed, initially say sort of diffuse, like the tori sort of starts moving, like dephasing essentially. So there is an understanding of how you get this gamma one.
Okay, yeah, it's very interesting. Just this is a kind of comment, but in the classical case, people looked at what they called the forced measurement situation, which is where you impose, you declare a distribution of measurement outcomes, and then you run the dynamics projecting into those, or with weak measurement analog of that. So I think this is effectively what you're doing here, because you're not using the information.
Yes.
So I think that it will probably then, it connects to that transition rather than the transition where you use the information.
Okay, yeah.
So you have to figure out the classical limit of using the information, using the Born update, basically.
Yeah, that's a very interesting.
So the
that's,
natural,
I think, correct. Yes. Yeah.
So I mean, so somehow in this case, the noise and dissipation satisfy fluctuation, dissipation, and it goes to equilibrium. So supposing I just take one oscillator with this kind of a noise, even a harmonic oscillator. So you're saying it will, at least at a classical level, it reaches thermal equilibrium.
Yes.
But in that case, supposing I look at the actual full quantum problem, I mean, would it? I mean, do you think?
Yeah. So actually, we have. I mean, I didn't show. So we have worked. I mean, worked out this on non-interacting case. So you can solve the steady state. So what you can show that you will reach this. So there I am not deriving Langevin equation. I am doing full quantum calculation with Keldy's-Green's functions. So you can show that they satisfy fluctuation dissipation with. There is some correction. So there is a frequency dependent temperature if you do in the quantum limit. If you take the classical limit, you find this result. So you are in the quantum limit, it will not satisfy this fluctuation dissipation. Yeah. So with the non-interacting case, we can solve exactly that. In fact, non-interacting case, even the entanglement can be calculated. This is not part of this work, but something that we are doing for the measurement process.
Any other question? Well, if not, then let's thank both the speakers again.